You can skip part B if the difference between continuous and discrete random variables makes sense to you. This is just another comparison between the two. So we have an experiment. Andre goes scuba diving at various locations, and when he steps off of the plane, he wants to figure out how much time until low tide when he can go scuba diving at a certain site. We assume low tide occurs every 12 hours. This appears to be a uniform distribution. No particular time from when he gets off the plane to low tide seems to occur with more probability than any other time. Now, if Andre only looks at the hours until low tide, then this would be a discrete distribution from 0 to 11. Here in blue is the cumulative distribution function. It appears to be not continuous because there's jumps in it. Therefore, this is not a continuous random variable. The probability mass function here is given in gray, and it looks like it should all be the same. Here it so coincides that the area underneath the PDF, or probability mass function, is also equal to 1. And the next example, though, here, if Andre starts taking into account the number of minutes and hours until low tide, and he rounds down, then we're going to break down each one of these hours into 60 parts. And we can zoom in on just that first hour and break that into parts. And here's my new cumulative distribution function. And it only matches up at 1 hours. The probability mass function now does not have an area of 1, but if we were to add up all the probabilities, then this would indeed have a probability of 1. So recall, we find the probability of a continuous variable using area, and the probability of a discrete random variable using summation, or adding up all the probabilities. Now, if Andre started taking into account the number of seconds until low tide, then the probability that he is any particular hour, minute, and second away from low tide would be 1 over 43,200. At this point, it would be much easier just to use the continuous uniform distribution. If we let x represent the hours until low tide measured to an arbitrary level of precision, then x has a continuous uniform distribution from 0 to 12 hours. Here's the graph of the CDF. The probability density function for this random variable would be graphed here. So f of x equals 1 over 12 when x is between 0 all the way up to 12 and 0 everywhere else. Since there's an infinite number of numbers between 0 and 12 hours, we can then say that the probability that Andre has any particular time away from low tide is 0. But we can now measure the range of values. For instance, the probability that he's between 3 hours and 4 hours would be the area of this rectangle, which has a height of 1 over 12 and a width here of 1. So he has a 1/12 chance of being between 3 and 4 hours away from low tide.